Mr. Chairman, honorable ladies and gentlemen, I'm a student from National University of Defense Technology. I'm honored and proud to have the opportunity to speak at this conference. Today, I'd like to present a summary of my paper, a Hashgraph-Based knowledge sharing approach for mobile robot swarm. My presentation will cover the 5 aspects. Let's begin with the part of introduction. A robot swarm is made up of a large group of locally interacting individuals with common goals, and it has been applied in many scenarios, such as path planning, site selection, and task assignment. A robot swarm is a self-organized system. Collaboration is the core task of the robot swarm, and the robots usually collaborate in a decentralized and self-organized way. With no central control node, individuals can take actions based on certain rules so as to emerge the ability to achieve task goals at the swarm level. Under this condition, how to enable the robots to collaborate efficiently on the swarm level? Many algorithms are proposed to improve the efficiency of robot collaboration, but most of them focus on how to manually preset the behavior rules of robot individuals. It's hard to unit the local behavior of each robot into a resultant force. In fact, common knowledge in a group of robots, the knowledge known by everyone or nearly everyone, can significantly promote the efficiency of robot collaboration. In a stable environment, robots can directly share knowledge with others to achieve common knowledge. However, the working environment of a robot swarm is dynamic and the communication range is limited. It's difficult for swarm robots to support global synthesis of information collected by the swarm. The question is how to achieve common knowledge under such condition. To achieve common knowledge, a lot of work have been done. They can be divided in 2 kinds, centralized and decentralized methods. These centralized methods, such as RoboEarth, OpenEarth, and RoboBrain, can offer common knowledge to the swarm, but the support of the centralized nodes, such as cloud or edge nodes, need to ensure the connection between the robots. The central node also has the risk of single point of failure. The consensus algorithm of distributed systems such as Paxos, Raster, PBFT can be applied to enable members in the robot swarm to achieve common knowledge. However, the classical solution to distributed consensus problems such as two-phase commit usually require frequent committing, responsing, and other interactions among a group of nodes. That is difficult to be applied in dynamic network topology, and nodes are often divided into several routes. It doesn't meet the requirements of decentralization. To solve this problem, the traditional blockchains can be adopted to provide the robot swarm with common knowledge in a decentralized way, and it has been used in many applications. However, proof of work, the consensus algorithm of blockchain, requires robots to keep solving puzzles constantly to add new blocks to the blockchain, which means that electricity will be wasted on extra computations. Besides, the blockchain forks may occur if robots find the solutions to the puzzles at almost the same time, or when blocks are not spread through the entire network, resulting in inefficient use of information and the resources. Here, we propose a novel peer-to-peer knowledge sharing approach for mobile robot swarms. This approach is based on Hashgraph, a data structure and a consensus algorithm. Hashgraph is made up of several nodes and many events. Each node maintains a local hashgraph The process of synchronizing their local hash graph is named gossip about gossip. When Carol randomly tells David everything she knows, David records the fact by creating a new event D4, which contains the hash of event D3 and C2. At the same time, David stores a timestamp and some transactions into the event D4. As the process of gossip about gossip goes on, based on the local hash graph, everyone can determine the consensus order of the events according to the virtual voting control. With no proof of work, Hashgraph allows the node to create many events per second, and it doesn't call for high computational power. Besides, Hashgraph is 100% efficient in information utilization because no events will be discarded. The contribution of this work is shown on the right. In this work, we enhance the gossip rules of Hashgraph and design the Hashgraph approach. The second part is motivated scenarios. Sometimes, a group of robots needs to reach consensus among several options, such as which working position to go. Sometimes they have to go to several positions, which leads to the problem of task allocation. The experimental environment is a square area containing several tiles. The fill ratio of light tiles to the whole area represents the feature of this area. The goal of the swarm is to reach a consensus on the value of every feature efficiently by exploring the area and sharing knowledge with others. The left square is a single feature scenario. The right one is a multi-feature scenario. It is produced by combining 3 single feature layers. We adopt the simulator for the kilobots. It is equipped with several light sensors that can detect different features, but it can only detect one feature at a time. In classical approach, the author proposed a decentralized strategy algorithm and a dynamic task allocation strategy. In their approach, while keeping working randomly in the environment, the robots alternatively explore the environment to estimate the feature and share the exploration results with local neighbors. Based on the shared knowledge, the robots make decisions on the feature. The feature switching strategy is that the robots switch to the least certain feature every time before exploring the environment. There is an advantage in decision-making time. In the next part, I will describe the hashgraph approach. In common hashgraph, a robot randomly chooses another one to synchronize the hashgraph. But in the mobile network, we stipulate that a robot can only choose its neighbors, as shown in the figure. At the first time, the left 3 robots are close to each other, so they gossip among themselves. The right 2 robots do the same, and then the middle 2 robots work to each other. They gossip between the two, and gradually the events reach consensus. But when 2 robots meet, they will synchronize the local hashgraph and create a new event to record this synchronization. Therefore, the synchronization process is the same way that an epidemic is propagated throughout a group of individuals. How long it takes for the infection to reach every process has been considered in the infect for every model. According to the formula, hashgraph can be synchronized among the whole swarm in a finite time. Now I will describe the hashgraph approach in the single feature scenario. The process of a robot exploring the area is divided into observation and dissemination state. In observation state, the robots work randomly around the area to explore the feature with its sensor, and then make an estimate about the feature. In dissemination state, robots send messages to neighbors to share his estimates and beliefs. During both states of a robot, once it receives a message from its neighbor, which means they are in communication range, it will synchronize Hashgraph with this neighbor and bundle the received message into the newest event. Once reaching a consensus on a group of events, each robot will make a decision according to the right two formulas. The two formulas demand that both the number of estimates and that of the beliefs are above the corresponding thresholds. The algorithm in the multi-feature scenario extends that for the single-feature scenario. Each robot maintains beliefs and makes decisions on each of the features with the same algorithm. The message also contains the estimates and beliefs of all the features. The difference is the initial distribution of robots on different features and the strategy of feature switching. With the results of the Hashgraph consensus, a robot can roughly figure out a variable that measures the difficulties of different features, and switch features according to the right two formulas. With the Hashgraph consensus, robots can get the common knowledge and act in accordance with uniform instructions. Even if the robot has made a decision on some feature, it may still be assigned to explore that feature to help others make decisions, which is the embodiment of self-organizing and collaboration among the swarm. Next, I will show the experiments. To test the efficiency of common knowledge produced by Hashgraph approaches under different field ratios, 30 robots are assigned to explore the single-feature environment. The performance of classical and Hashgraph approach are compared. According to the figure, in both approaches, the higher the field ratio, the faster they make decisions, and they reach a consensus on the right decision over all of the field ratios. When the field ratio is less than 0.6, robots of the Hashgraph approach can reach a consensus faster than that in the classical approach. But the robots in the Hashgraph approach start to make decisions at a much later time than those in classical approach, because the time is delayed by the process of gossip about gossip and virtual voting, but the curves rise at a much faster slope. In the multi-feature scenario, we set the three features to red, green, and blue. There are 4 different initial distributions, equally distributed and all distributed to one of the 3 features. Compare the curves. We can see the robots in the Hashgraph approach start to make decisions at a relatively later time, but finally they reach consensuses on all of the 3 features in 120 minutes. While the robots in the classical approach even can't reach an agreement in 150 minutes. The picture shows the distributions of robots on 3 features over time. In the classical approach, we can see that there is a problem of over-adaptation with the approach. The curves rise and fall frequently and the ranges are large, which means that some robots switch between the 3 features repeatedly, leading to a waste of time and battery resources in practice. On the contrary, the curves of the Hashgraph approach are much stable and fluctuate in a small range. This is due to the common knowledge achieved by Hashgraph. Despite the limited communication range and the dynamic network topology, Hashgraph can still help robots achieve common knowledge to coordinate their actions well on the swarm level. In these experiments, we evaluate the performance of the Hashgraph approach under different moving speed and communication range. As can be seen, in the case of the same communication range, the greater the moving speed, the shorter the time to reach a consensus. But the difference is relatively small. On the contrary, the communication range has a great impact. When the communication range is limited to 100 mile-meters, the swarm can reach a consensus in more than 20 minutes, while if the communication range reaches 1,000 mile-meters, it means that robots can reach almost every member of the swarm. The time is less than 2 minutes. In fact, in the traditional blockchain, the consensus time depends more on the speed of mining new blocks, while the communication range affects the broadcasting speed of newly mined blocks. In this part, we investigate the resource consumption of blockchain and hashgraph approaches by counting CPU utilization. The blockchain approach is based on Ethereum, and the difficulty of mining new blocks is set to a reasonable value. The experiment is carried on a personal computer. The configuration is shown on the right. The CPU utilization of the blockchain approach starts at about 80% and keeps for about 40 minutes. After that, the curve rises rapidly and reaches its top about 350%. This is caused by two factors: mining new blocks and dealing with forks. The CPU utilization of the hashgraph approach keeps at about 80% from beginning to end, so the hashgraph approach consumes less resources than the hashgraph approach. In the last part, we summarize the results of the experiments. To address the shortcomings of traditional blockchains in achieving common knowledge among mobile robot swarm, we propose Hashgraph as a knowledge-sharing medium for the mobile robot. With the enhanced Hashgraph, we demonstrate that the Hashgraph approach can help robot swarms reach consensuses and realize task allocation efficiently. The results also show that the Hashgraph approach requires less computational power and has higher resource utilization than traditional blockchain approach. Thanks. The above is a brief introduction to my paper. If you have any questions, you can contact me via the email.